Can everybody see the big picture of the power supply? All right, so as we're looking at the big picture of the power supply, there's a couple things I want to bring to your attention. And it goes to show the outlet way over on the left-hand side is your typical AC wall outlet. It has your two prongs and it has the ground lug, okay? So those are the three things that you will see in a typical AC outlet. I'm interested only in the two prongs right now. And so the two prongs are connected to this connector here, and they will go to the very first part of the power supply, this thing called T1. So your power supply, as I've shown in this diagram, is divided into different modules. And I have a module, there's a module and a function and devices that are used. So if you take a look at the first module of the power supply, the function, and what are the last four letters of the word function? T-I-O-N, is that correct? Okay, so function ends with the last four letters T-I-O-N. The very first module has what function? It is called transformation. Transformation ends with what four letters? T-I-O-N. You'll see a pattern that will happen with this. The second module is what type of function? It's called rectification. The third one is called filtration. And the fourth one is called voltage regulation. And the fifth one is called protection. So each one of these modules ends with the same four letters. So when you see this in quiz form, test form, the next time we meet, we will have weekly tests, count on that. That one of the things that can help you remember the functions is that for sure, they all end with T-I-O-N, okay? Made it easy for you. If you take a look at the very left-hand column, it goes to show devices. It has a heading showing devices that are used in each of the modules and also states what their purpose is. I go to show the input waveform that is going to go into your power supply. The input waveform is an AC waveform. It is what is measured at the wall outlet. At the wall outlet, you have 120 volts RMS, which calculates to be how many volts peak? Where's your calculators? How do you calculate the peak voltage from RMS? You hadn't done that since ESYS 50. Pull out your calculators, figure it out. I'm looking for a peak voltage quickly now. 169.71 volts peak. 0.71, okay, not 73. Okay, so if we're starting with 120 volts RMS, you multiply that by, divide by the square root of 0.5, yes? Yeah, don't use 0.707. Yeah, use the square root of 0.5 as a far more accurate calculation. Now, that being said, so this waveform is 169.71 volts peak. That's what PG&E promises to deliver to us on those wall outlets. It'll vary some. When you go to measure, we won't always measure 120 volts RMS. And a lot of times we'll measure 118, 117, sometimes 121. Isaac, you had a question.
When I did it on 131.
You take 120, divide by square root of 0.5, and then hit equals. Okay. All right, so this is what you have in part A. Part A is an AC waveform. And now take a look at where part A is in the diagram. Part A is on the left side of T1. You have a waveform at part A, and the waveform on the left side of T1 is the full 169.71 volt peak AC waveform. Very often in your power supplies, you will have an F1. What's F1? It's a fuse. And what's S1? S1 would be a switch. So very often your power supplies will have some kind of a switch. Now, this is what's being presented by the wall outlet. Take a look closely at module number one. Module number one, the function we stated was transformation, yes? What is the device that is used to accomplish this? What kind of transformer? iron core transformer. These things are heavy, okay? And what is the purpose of the first module? What is the purpose of transformation?
It lowers the voltage by increasing the.
Yes, it lowers the voltage, and conversely, it will increase the current. Now, the terminology that we use with transformers has to be this terminology. The transformer that I'm showing in this illustration is called a voltage step down, current step up transformer, okay? So that's the terminology we use. What type of transformer is it? You have to say both parts of that sentence. Voltage step down and current step up transformer. And if you take a look at the waveform at B, does the waveform at B look smaller? Okay. And the purpose of this transformer is to bring that voltage down to a safer level for us to use. And the waveform is subsequently a smaller waveform. This is still AC. So you put AC on the input side of the transformer. You get AC on the output side of the transformer. So the only thing that happens with the AC is it's still AC, but the voltage is now less. You'll see that the current goes up, but that's a separate calculation discussion we will hold for the time being. Now, what is the module number 2? Module number 2 is identified with what function? Rectification. Everybody get used to saying the word rectification. Yes. Rectification uses what devices to accomplish this? They are called rectifier diodes, not just any diode. You can't use LEDs. LEDs are diodes. You cannot use LEDs. You cannot use Schottky diodes. You cannot use any high-speed switching diodes. You have to use something very special called rectifier diodes. So these are special diodes. You can't use photodiodes. They're also diodes. You have to use rectifier diodes. And rectifier diodes are very special diodes that are designed to function at low frequencies, 50, 60 hertz. Why 50, 60 hertz? Because that's what PG&E gives us. What PG&E gives us in this country, 60 hertz. But other utilities in other countries around the world may offer 50 hertz to their customers, yes? So the two world frequencies for AC power will be either 50 hertz or 60 hertz. If you take a look at what happens with the rectifier diodes, what is their purpose? Their purpose is to do what in module number 2? Converts AC into DC. Now take a look at the waveform C. The waveform C right here, does that look like DC? Isn't DC supposed to be straight line? Well, how come this isn't straight line? How could you call this DC? It's got humps in it. What makes the waveform C? How can waveform C be called DC when you compare it to waveform B? It's got humps in it. Who can explain that? Any thoughts? Chase says, given the illustration that I've drawn, the negative half wave, the negative half cycle, has been removed. So only one polarity remains. So regardless of whether it's straight line or whether it has humps or bumps or waves, as long as it's on one side of the 0 volt line, it's either positive DC or it's going to be negative DC. And there's a name for this waveform that we see in waveform C. Waveform C is called specifically positive pulsating DC. Everybody repeat. Positive pulsating DC. That's the official name given to the waveform. If we removed the other half of the waveform, if we remove the positive half and retain the negative half, then we would have a waveform called negative pulsating DC. But in this case, because of how the diode is arranged, we have positive pulsating DC. So it has been changed. It has been converted. The waveform has been converted from AC now to DC. And the output of this waveform from the rectifier now goes where? What's it say at the bottom of this module number 2?
The output waveform will be rectifier equals input waveform.
Yes, the output of this module is the input to the next module. Okay? And look at where waveform C is measured. If you take a look at the diagram up here, waveform C, doesn't it come after the diode? So what we measure at point C with an oscope is going to be, in this case, the waveform shown as positive half wave, pulsating DC. And this also happens to be the input signal going into the next module. Take a look at module number 3. Module number 3 is called what function? Filtration. Ends with what 4 letters? TION. What type of device is used to accomplish this? A filter capacitor. Okay, filter capacitor. You can't just use any old capacitors. You have to use something very specific, and the most effective ones that are used by most power supplies are some sort of an electrolytic capacitor. Okay, some sort of electrolytic capacitor. And what is the purpose of this module? Module number 3. There happens to be 3 bullet points. First bullet point. Could you read that, Isaac?
Smooth out DC pulsation.
It smooths out the DC pulsations. First and foremost, if you take a look at waveform C and you compare it to waveform D, does waveform C kind of remind you of the speed bumps that certain streets and neighborhoods put in the middle of their roads? They put these speed bumps. And what filtration does is it smooths out those bumps. And so you have waveform D still has bumps, okay, but they're smoothed out. It'd be a whole, if you were a car driving down the street, your suspension would love you more with waveform D than waveform C. Waveform C would be killing your suspension. Okay, waveform D, you'd feel a little jiggle. So that's first bullet point. Second bullet point for module number 3 just does what? Reduces the V ripple, okay? Voltage ripple or ripple voltage. It's spelled V rip or V ripple. It is spoken as ripple voltage, okay? And what is ripple voltage? We'll talk about that I'll tell you right now. If you take a look at waveform C, ripple voltage is the difference of voltage between the positive peak and the 0 line. That entire bump, that entire peak is ripple, whatever that works out to be. If it's a 40 volt peak, then it's 40 volt ripple, okay? So ripple voltage for these waveforms is defined as from the top of the peak to the bottom of the valley, if you will, of the waveform. Now take a look at waveform D. If you take a look at waveform D, where is the peak? Right here. Where is the valley? Right there. Isn't that less the difference between the peak and the valley? The peak and the valley is your ripple voltage. And have we, by virtue of using the capacitor, brought that ripple, reduced the ripple voltage? By smoothing out the waveform, we in turn are able to see less ripple voltage. How this works, we will talk about in much greater detail when we get to that particular part of the power supply. Next, third bullet point. Suarez, can you read that, please? Increases the effective DC output voltage. If we were going to measure, because if you go back to waveform C, this is positive pulsating DC, yeah? This is what we would see. This is waveform with the bump here and a flat spot here and a bump here. This is what you would see on an oscope. Well, suppose you hook a DMM up to this. What would it measure? It would measure, if you would, take a look at this picture, the waveform. If you imagine if this red line were a flexible piece of string, and if you could flatten it out, the amount of space underneath this curve, flattened out over a straight line, is about 1/3 of the way up, okay? So the effective DC here in waveform C is approximately 1/3 of the way up. If you take a look at the DC here, The DC would measure halfway between the peak and the valley. If the peak is here and the valley is here and the DC is right in between, wouldn't that be higher than in waveform C? Okay, that would be higher. So filtration does three very powerful things for us. Number one, it smooths out the DC pulsations. Number two, it reduces the re-ripple. And number three, it increases the effective DC output of your circuitry. What's to say at the very bottom, the output waveform from the filter equals the input waveform to the regulator. So take a look at where D is in the schematic. Whoops, lost it there. Let me come back. Is back there, coming back. Am I on the share? Okay, I'm not on the share. I will move this. Okay, we can see it on the screen, yes? All right, nicely shared. So if we take a look at where waveform D exists in the schematic, it exists after the capacitor. And after the capacitor is going into this rectangle, and in the rectangle, I've got this labeled as what? IC voltage what? Regulator. What does IC stand for? Integrated circuit. Okay, so there's a lot of microcircuitry in that. Okay, integrated circuit. And voltage regulator. So something having to do with regulating voltage. Let's explore that, see what this is about. So in module number 4, the name of the function is called voltage what? Regulation. What are the device or devices that could be used to accomplish voltage regulation? There happens to be 2. Could you read those for us, please, Jess? Yes, you have something known as Zener diodes, very special diodes. You don't use Zener diodes as rectifier diodes, they're totally different. But Zener diode is a very special diode that can be used for voltage regulation, and we will discuss that in greater detail when we get into Zener diode and voltage regulation. Then the second one, as you've read nicely, is IC voltage regulator. An IC voltage regulator comes in a couple of different packages. We can show you some during a little later on this evening. And what is the purpose that is accomplished in module number 4? Can you read that for us, please, Jeremy?
To hold DC output voltage constant under changing circuit conditions.
That's really important, under changing circuit conditions. That is the fundamental difference between your battery packs and a voltage regulator circuit board. For those of you who were with me for ESYS 50, I had assigned the students to purchase their circuit boards that had DC power supply on the circuit board, breadboard, yes? And what was different about that versus previous semesters where I had battery packs? The difference was with the battery pack, the batteries drain. They don't give you consistent voltage. You start off with 3 AA cell batteries, each one rated at 1.5 volts, giving you a total of how many volts? 3 AAA batteries in series gives you how many total volts? 4.5. And it will give you it will give you more than 4.5 with the new battery pack. You might have 4.6, 4.7, but over a period of time, it will drain, and then it'll become 4.5 and 4.4, 4.3. No, so you could not rely on the battery packs to give you a consistent 4.5 volts for your experiments. So I was able to find a kit that luckily had packaged in it a regulated DC voltage supply. And you have a choice of 5 volts, fixed 5 volts, or fixed 3.3 volts. And what is effectively different about the IC voltage regulator, the voltage supply that has voltage regulation, is that voltage will remain constant. It will be steady. Take a look at the power supplies at your stations in front of you. Why are these instruments well over $1,000 just for the power supply? Okay, the reason why it is built rock solid, and it will maintain that voltage going out to your experiments regardless of varying load conditions. Okay, and that's what the description of the purpose says. The purpose says to hold DC voltage output constant under changing circuit conditions. And take a look at the waveform E. Is waveform E now a straight line? It's a rock solid straight line. Is there any peak or is there any valley that you can discern on that? Not from this picture. Do you think your ripple voltage will be less? Almost non-existent in this particular picture. And do you think your effective DC is now even higher? It's at the peak. Whatever the peak was before, it is now that value of DC. Okay, so it's as high the DC as you're gonna get is coming out of the voltage regulator. What's it say at the bottom of module 4? Output waveform from regulator equals input waveform to the protection module. So take a look at module number 5. The function is called what? Protection. And what type of devices do we use for protection? They are listed as fuses, circuit breakers, and other transistor circuits. Now notice how I abbreviated transistor. Transistor is an XISTOR. And very often the letter X is substituted for TRANS. So that is a valid abbreviation for transistor. Same thing with transformer. I could put the X in front of former and we would understand that it is a transformer. What is the purpose, Mr. Montano?
Power supply in or load from any current.
Yeah, it protects not only the power supply, but also protects the load from what? Overcurrent conditions. What could cause an overcurrent condition? Could be shorts. Typically, it would be something short-circuited. And then at the bottom of number 5, the output waveform from the protection module is the input waveform to your load. So there, my friends, is the big picture of the power supply. Okay, hold this to your hearts. You will see a quiz on this next week, and you'll be asked to identify what is the purpose of module 2. You may see the schematic, and I might point to something and say, okay, tell me what this does. Tell me what is the function. Okay, tell me what is the device. All that is spelled out for you in this. Are there any questions? Open notes for, not to this piece of paper, but if you take the time to write this into your journal, yeah, okay. Wow, better update that journal. Okay, okay, good job. All right, any other questions regarding the big picture of the power supply? All right, let's go ahead and pause, hit stop share. Okay, I have this back on the record. So if you'll take a look at your lab activity 1 power transformers, lab activity 1 is not a hard activity at all. It's a very, very fun activity. It's very specific, and you are required to do certain things. You will be working individually in this exercise. So everybody gets their hands on all aspects of this lab. And what it introduces you to is going to be, if we look at the lab parts, we're going to need a wall wart. We're going to need this with a 12-volt secondary. It'll come from Janko. We're going to need how many multimeters according to this list? 2 multimeters. One's going to be measuring what? AC volts. The other one's going to be measuring what? And then what else are you going to have? A kilowatt power monitor, and then we will have PC and multisim later. And you're also going to have what? Load resistors that are going to be determined by the student, and AR will be as required, okay? Okay, and so if we take a look, there's an introduction. The introduction walks you through what wall warts are, and here is a wall wart. Okay, this one happens to be a rather large wall wart. Your cell phone wall warts are typically going to be smaller than this particular guy. This particular guy is rather large and heavy because it has a lot of output current capacity, and you would read on the label, let me focus right here on the label. Everybody see that clearly? Woohoo. All right, so here is the plate that marks the specifications for your power supply. As you are looking at this power supply, what is the input voltage here, Isaac?
120.
VAC is how you would read that. 120 volts VAC, and it is 60 hertz, which is the cyclic rate. And what is my current? Isaac?
1500 milliamps.
Input.
Input?
Yeah.
0.4.
Everybody see that clearly? 0.4 amps. All right. Now that's on the input side. Now take a look at the output side. What do you see there? Montana? 12 volts AC. And how about the current on the output? 1500 milliamps. That's 1.5 amps of current coming out. That's potentially lethal. Are we clear on that? You are going to be working with potentially lethal voltages and currents. And so I want you to exercise utmost care when you go to do this particular exercise. No burning up of the components, no burning up of the meters or the leads, no burning up of the power supply, and certainly no injuring yourself. Okay, so do your best to follow all the directions of the experiment. So this is the wall wart. This is the label side. You have the plug side. You have one of these guys. Then what it is that you're asked to do is you're asked to use this in conjunction with our kilowatt. So this is the kilowatt. We've used this previously in ESYS 50. And what the kilowatt does is it plugs into a power strip in order for it to be powered. And then whatever device you plug into here, this will be able to measure various quantities. It'll measure the voltage that's being used by the device plugged in. Could be a refrigerator, air conditioner, could be anything. It'll measure the current, it'll measure the watts, the volt amps, the hertz, it'll measure power factor, kilowatt hour. So it'll measure all different kinds of things. It's a very handy module. So this particular guy will plug into a power strip. You will then, at the appropriate time, take this to plug into here for the experiment. Fundamentally, as you go through different steps, you will be asked to use your digital multimeters. You're going to be asked to measure the ohms of the primary, and the ohms of the primary are attached to these two prongs right here. And the ohms of the secondary are going to be able to be measured on the output side, which is this plug right here. So very often, this is what you're going to plug into your electronic keyboard. This is what you could be plugging into your Nintendo gaming device. It's a very standard wall-wart power supply apparatus. So you have AC coming in here. And more often than not, with most power supplies, they're going to be converting AC to DC. This is not an AC to DC converter. This is an AC to AC converter. Why are we using AC to AC converter? Is because we want you to see the transformation that takes place from the input to the output. If I were to hook up oscope leads to this, you would be able to see the waveforms. Input is larger, 169.71 volts peak, and the output is smaller, 12 volts AC, okay, which would work out to be 16.97 volts peak. And you would be able to measure that between the inside pin and then the ring on the outside. To make things easy for you, Nabil has fashioned from previous labs this particular adapter, and this particular adapter plugs right in here, and it has two wires for you to use. There's a wire here, and it has a wire here. Do not, under any circumstances, touch these two wires together. It would be catastrophic. It would lead to automatic destruction of the transformer and possible injury to yourself. Do not handle the bare wire ends of these without using your insulated rubber gloves, latex gloves, nitrile gloves. The experiment will ask you to measure the ohms of the primary. So you put the ohm meter onto these prongs. It'll ask you to measure the ohms of the secondary. You put the prongs here. None of this is plugged in for this part of the experiment. And then it'll ask you to measure the ohms between one of the prongs of the primary and one of the wires of the secondary. And you're going to record that value as well. Then what you're going to do is you will then take your power strip. And so your power strip will be any one of these devices that you have outlets underneath the benches. Take this particular guy, plug it in like so, turn on the juice, and your kilowatt will tell us what is the starting voltage that is available to us, how much amperage is flowing, what type of watts, if any, or voltamps is being consumed in this process. So fundamentally, basically nothing. You will then make sure that these ends are not touching anything, okay? These cannot be touching anything. You will do the appropriate calculations based on the parameters of the exercise before you even plug this in. You're going to do the appropriate calculations for the resistor value. And I'll write down the values for you and give you the power formula so that you can do the calculations. Once you determine the appropriate value of the resistors, you're going to have two resistances. How many resistances? Two. And you're going to be calculating these using Ohm's law and Watt's law. And if I go to do this very quickly for you, I'll do this right here. Woohoo, came back, yay. Amazing. Quick focus. There we are, nice. All right, so you always have had VIR for Ohm's law. In addition to Ohm's law, you had three additional circles called Watt's laws. And for Watt's laws, what were the formulas that we used? The most common one is PIV, yes? What's the next one? P what? Come on, you guys were in 50 not that long ago. Somebody give this to me. I squared R. Then the next one has a P here. V squared R. There you go. Thank you for remembering. Ah, that was a quick test. All right. So you can use these formulas, and each one of these circles will give you three other formulas. So from all four circles, you have a total of 16 formulas that you can derive. Well, 3, 3, 3, 3, 3, 3, 3, 12. You have a total of 12 that you can derive off of these four circles, yes? Okay, cool. Now, you will be asked to determine the value of R. So you can determine the value of R in only two places. This is one where power and resistance are part of the circle. Here's another one where you have power and resistance as part of the circle. You will be using this particular one because you'll have the voltage, you'll be specified the power, and you're going to have to determine the resistance, okay? So your resistance then would be equal to what? If I'm looking at this particular circle here, how would I derive the formula? How would I derive the formula from here for power? I'll put my finger over the R. What's left is V squared divided by power, right? So here's your V squared divided by power. So if you know your power is going to be one of two values, because one of those values will be 1 watt, And in another instance, it will be 6 watts. So all you need is to determine the value of voltage in each of these cases in order to determine the resistor that is needed for each of these power values. Yes, does that make sense? Okay. When you go to do this, whatever value of resistor you calculate, you're going to need to be concerned that if we're working with 1 watt and you're working with 6 watts, these are very high wattage resistors. What are the largest wattages you have used on your resistors so far, Chase? Or the ones that you've used on the boards for the past bunch of semesters? What's the highest wattage you've ever used? If you've not paid attention to them, you're going to need to learn how to pay attention to them now. All right. Jeremy, you think?
I have used mostly
Quarter watt and half watt resistors. Okay. Are they relatively small? Quarter watt and half watt resistors are relatively small. Guess what? You're asked to play with 1 watt and 6 watts. If you use your quarter watt and half watt resistors, whatever ohms you decide may be the right ohms, but if you don't have the right power dissipation, what's going to happen with your resistors? They'll burn out pretty quickly. So guess what? You're going to use high power dissipation resistors. And what they look like is something like this. Okay, these are high wattage resistors. Now, for the ohms that I calculated, this particular set of 3 worked out properly. This ohms plus this ohms plus this ohms worked out to give me the total ohms that was pretty close to my calculations. All right, but these are high wattage resistors by virtue of the fins. This is an aluminum body, so aluminum dissipates heat really well. And they're finned, just like the fins of your motorcycle engine or the fins that you find on a gasoline-powered lawnmower. They dissipate heat really well. Well, if they put the fins on the body of this resistor, it'll dissipate heat pretty well. Guess what? It'll dissipate heat so well, it will melt. It will melt the latex of or the nitrile of your gloves. It will burn your fingers. So when you go to do this experiment, you want to make absolutely sure you hook up for the shortest period of time possible. You make your measurement in the shortest period of time possible. You write down the values as quickly as possible. Then you disconnect. Because the longer you leave the wall wart in place, if I connect these wires right now, these wires that we have, and I go to connect them here and hook them up with my voltmeter or my ammeter, these will get hot. And they will get so hot that it can burn you. So it will get hot, but that's why you want to make your measurements very, very quickly, okay? And you're going to be measuring voltage and current simultaneously, which will require, my friends, you to use 2 sets of digital multimeters. You will use one multimeter as a voltmeter, and you will use the other multimeter as an ammeter. So one will be set up here, and another one will be set up here. Turn this puppy on. This guy is on. Raise this guy up. I get maximum view on these guys. You can see what's up. So is this guy set to measure AC voltage? It's on. Let me focus. There. Nice. AC voltage, and this is set up to measure voltage. Red is on V, black is on common. Is this guy set to measure current? AC current, milliamps. And is the red over to the milliamp connector, and is the black on common? So you got to get your meter set up so that they're ready to go. Is this set up to measure AC? Is this set up to measure AC? Nope. What do I need to do? Hit the select button right there. And that's how you, if you say these meters are not measuring what they're supposed to measure, I come over, and if I see DC there, you're going to get a little rap on the head, right? Because I'm reminding you right now, AC, AC, if you leave it on DC, you'll get erroneous results. Now, that being said, we move these guys apart, and when you go to hook this up, I'm not going to plug in the wall wart now because I don't want anything to heat up. When the wall wart is plugged in, you will have these wires ready to go. So the measurement is done this way. If I'm going to use 1, 2, or 3 resistors, first thing I want to do is I want to hook up my leads for voltage. So I'm going to hook up right across here and here. When I go to hook up my wire for this side, and I go to hook up my wire for this side. So if this were on, and I'm giving a little bit of tension here by pulling on this slightly, and that way I'm guaranteeing I have good electrical and mechanical contact of the wires on either end, I'm going to be able to get current through these resistors and be able to measure a voltage using these connections to this meter, yes? How do I measure current? I have to break the circuit open, yeah? No, I'm not going to break it open where these are nicely soldered. I'm going to break it open at either that end or that end. But before I even talk about that, does it matter which polarity goes where? Should I have the red on the right or should I have the red on the left? Should I have the red on the right or should I have the red on the left? Ivan? Doesn't matter why? I'm measuring voltage. So if I'm measuring, if I were measuring resistance, you're right. If I'm measuring resistance, it doesn't matter. But here I'm measuring voltage. So if I'm measuring voltage, should I have the red connector on the right or should I have the red connector on the left? Ivan? So what would happen if I did this? It froze, sorry. Press and hold. Okay, so what would happen if I put the red on the left side and the black on the right side to make my measurement of voltage? I would have the opposite polarity, voltage. How many people agree? Montano agrees, Jeremy agrees, Jess agrees. Morris, what do you think? And Chase? What's that? A little louder so everybody can hear you're right and they're wrong. Does it not matter because it's AC? Think about it. It doesn't matter because this is AC. Yes, it's going to read a value with no negative sign here because this is AC. So it makes no difference which side you put the red. Are we clear on that? All right. Now that being said, now let's go ahead and bring in the ammeter. Now the ammeter is here, and in order for me to measure current, I have to break the circuit open. How do I break the circuit open? Now keep in mind, if my wall wart was plugged in, I don't want this on here for any extended period of time. So I'm going to do this. I'm going to leave one end connected, like so, and twist and lock that as best as I can. And I'm going to introduce between, oops, could you get that for me, please? Thank you. I'm going to introduce, thank you, between where this wire normally would have hooked up for voltage. I break the circuit open. Have I created an open between this wire and this resistor? Are we looking at this? I have an open between this wire and this resistor. So I will hook up one here for the ammeter and the other one here for the ammeter. Now is my ammeter in series with the electricity flowing from the wall wart wire through the ammeter, through the resistors back to the wall wart. Have I completed the circuit? Is my ammeter in series to measure current? Yes. And is my voltmeter across the resistors to measure voltage? Yes. So while this is all connected right now, very quickly, I'm going to connect this into my wall wart. And lo and behold, do I have some values? I'm measuring what voltage do you see here? 12.81 volts. And I am measuring how much current here? 83 milliamps. Once you see these values, disconnect, okay? Don't leave it on for any extended period of time. marveling at the wonder of your connections. Oh, this is beautiful. I'm going to pick up my cell phone. I'm going to take pictures of this, selfies, show mama. Yeah, I can do that if you take pictures fast enough. And I encourage that. That's really a lot of fun to share your lab work with your family. But truth be told, we don't want these things to get so hot, especially the singular one. If I have three, they're going to dissipate heat, they're going to get warm, but this singular one will get hot, and the singular one will burn you if you're not careful. So is everybody understanding the connections that are necessary to make this lab work? Voltmeter is measuring across. Ammeter has to be part of the current path from the wall wart through the ammeter, back from the ammeter to feed your string of resistors, and then back to the wall wart. Okay? Okay, so after you do this part, this won't take very long, part of the exercise is you need to determine what the ohmic values are for that you're going to need, and then you're going to have to sign out for all of this from Nabil. After you do all of this, then there are some multi-sim exercises which we will talk about later. But are there any questions right now regarding what you're going to be doing for this lab? Okay, if not, I will go ahead and pause this recording and let you all go at it.